Welcome to Bright Mind Academy. Today, we are going to be working on the first video on our series of videos that will be on mechanics and properties of matter. Let's dive in. The first topic we'll be talking about will be the first topic in the JUPEB syllabus, which is measurement, quantity, and unit. This topic will help us to understand the building blocks of physics, which are quantity. Let's dive in. By the end of this lesson, we should be able to define measurement and physical quantities, identify the types of physical quantities and their definition, be able to give examples and also differentiate them, identify and use SI units for common physical quantities, perform unit conversion, and have a deep understanding of dimension analysis and be able to apply it, especially when you are given application question, which is what JUPEB like to ask about a lot. Let's get started. Okay, what is measurement? Measurement is the process of determining the size, length, or amount of a substance. Typically, using an instrument or a device, provide a quantitative description of that physical quantity. For us to be able to measure something, we must get to know about the thing must be a physical property, a physical quantity. Getting to know about the property of a physical quantity is what refers to as measurement. Measurement is very crucial in physics because they are the fundamental of conducting experiment and validating theories. Measurement is the backbone of physics. Without measurement, most of the concepts in physics will have been abstract and will have been very difficult to understand, and most of them might have not existed. Because if you are unable to measure the speed of light to be particular to be 3.0 exponential 8 meter per second, how will you be able to compare it to the speed of sound? We just know the light is faster than sound, but we will not be able to know the proportionality. That's one of the importance of measurement. Measurement is extraordinarily important to physics. The measurement begins with identification of phenomena known as physical dimension, such as length, perimeter, diameter, and so on. Measurement is very important. We do it every day. You measure the amount of water you take, the quantity of food you are eating, the amount of money you are spending on petroleum, the number of pens you use in a month, and all those things, they are all measurement. The quantity of electricity you consume, like if you just look around you, you see everything you are doing with your life is all about measurement. Even the number of days you are spending, the number of years you have spent on earth is also about what measurement. You are counting you are measuring the number of hours, the number of times you have spent, the number of time you spent in class. They are all measurement. Moving on, what is a quantity? Yes, we need to understand and be able to define what is a quantity also. A physical quantity is the property of an object that can be measured. The property that a particular matter has, and we can measure it. That property is a physical property. Basically, in physics, physical properties are divided into two. We have the fundamental quantity and the derived quantity. The fundamental quantities, they are like the bedrock. They are the raw material from which all other quantities are produced. They are the basic quantity from which all other quantities are derived. They are like the sand, like the cement, like the water needed for the construction of a building. Without them, we cannot have a building. They are very essential. They are the bedrock. The SI unit is built around them. That is trying to tell us the SI unit is the unit of what? Fundamental quantities. The fundamental quantities are 7 in number, which include the length measured in meters. We have our mass measured in kilogram, the time measured in seconds, electric current measured in ampere, temperature measured in Kelvin, amount of substance measured in mole, and luminous intensity measured in candela. The derived quantities are those quantities that can be obtained by simple combination of two or more fundamental quantities, e.g. force. Derived quantities, they are like the finished product. We get them from what? From the fundamental quantity. Let's take a look at force, for example. Force is the product of mass, which is a fundamental quantity, and acceleration. The acceleration is the derived quantity from what? The acceleration is derived from displacement and time. The combination of displacement and time give us acceleration, and the combination of acceleration with force, with mass, give us our force. Pressure also, which is the ratio of force and area. The force, as we have described, is a derived quantity from mass and acceleration, while our area is the product of what? Length, which is also a derived quantity. Another example is for work, energy, velocity, speed. All these are examples of derived quantities. I hope by now you have been able to know the definition of quantity, derived quantity, fundamental quantity, and you are able to differentiate between them. Now, let's dive in and take a deep analysis of dimension and have a deep understanding of dimension analysis. Let's talk about dimension analysis. Dimension analysis is a mathematical technique we use to convert units, check unit consistency, and simplify calculation by analyzing physical quantity. The dimension of a physical quantity is the power to which the fundamental quantity must be raised to represent the given physical quantity. The dimension of the physical quantity, since we all know we have the 7 physical quantity. The dimension of length is represented with capital letter L, that of mass with M, that of time with capital letter T, electric current with capital letter A, and temperature with K. Right? Moving on. Luminous intensity is represented with CD as what? As dimension, while amount of substance is represented with mole as the dimension. Okay, let's take a look at some example. This question is asking us to determine the dimension of the following quantities. If you take a very good look at this example, all of them, they are derived unit, they are derived quantities. Now, let's get started. The first one is velocity. Velocity, yes. Velocity, which is the ratio of displacement to time, right? So, displacement, which is a form of what? Is a form of distance. So the dimension will be what? That's length. Yes, thank you. L over, and what's the dimension for our time? Capital letter T. T. Therefore, the dimension for velocity will be what? LT raised to power minus 1. Yes, that's it. Moving on. The second one is what? Acceleration. Our acceleration A is equals to the ratio of change in velocity per unit time. And we have known the dimension of our velocity to be what? What do we get it as? LT raised to power minus 1. Yes, that's correct. And that of our time will be what? Capital letter T. Therefore, with this, we can get our dimension for acceleration to be what? LT minus 1 over T, which will give us what? LT raised to power minus 2. Simple. The next one is what? The surface tension. Surface tension. The next one is surface tension. Surface tension is the ratio of tangential force and length. The ratio of tangential force and length. Surface tension is the ratio of what? Tangential force and what? And length. So we need to first get the dimension for our force. Okay, what will be the dimension? What is the formula for force? Force is mass multiplied by acceleration. We have known the dimension of acceleration to be what? LT raised to power minus 2. And that for our mass will be what? The capital letter M. Therefore, our force will be what? Capital letter M multiplied by LT raised to power minus 2. Therefore, our force will be what? Capital letter M LT raised to power minus 2. Now, let's get the dimension for surface tension. Our surface tension ST, which is the ratio of force. And what's our force now? M LT raised to power minus 2 over length. What's the dimension for length? Our L. This L will cancel this L. Therefore, the formula for the dimension for our surface tension will be what? MT raised to power minus 2. Simple as that. Moving on, what is the third one? The third one is what? Force. We have done force under surface tension, so we are skipping that. It's pressure. What is pressure? Pressure is force per unit area, right? Yes. Pressure equals to force over area. We have gotten the dimension of force to be what? M L T raised to power minus 2. And that of our area will be what? L squared. That is length times breadth. They are both what? They are both dimension. They are both a unit of distance. So it will be L times L, which will give us what? L squared. Therefore, our pressure will be M L T raised to power minus 2 over L squared. This L will cancel one of the L here. And we are going to have our pressure to be equals to M T raised to power minus 2 all over L, which will also be equals to M L T M raised to power minus 1 T raised to power minus 2. And that will be the dimension for our pressure. Okay.